let me finish with deriving the estimator of the variance of the error term. Okay, so maybe start. Okay, so we know that yi is equal to xi beta plus epsilon I. Okay, this is the first assumption. The second assumption is that xi is non-random. But then we are assuming that expected value of epsilon I is equal to 0, and then we are assuming as well that the variance of epsilon I is equal to sigma squared, and the covariance to do is that we have derived the OLS estimator. Okay, the formula for this estimator is x prime x inverted x prime y. And what we have shown up to now is that the expected value of b is equal to beta, so the OLS estimator is unbiased. And also we have shown that the variance of the OLS estimator is equal to sigma squared x prime x inverted. Okay? And what I have said is that this formula gives you the variance of the OLS estimator, or ordinary least squares estimator. So it is the measure of precision of the OLS estimator. But the problem with this formula is that we don't know sigma squared. Okay, sigma squared is additional parameter which is unknown and which have to be estimated. Okay, and last lecture we have shown that the estimator s squared, which is given by the formula the following formula: the sum of squares of residuals divided by n minus k, where n is the number of observations and k is the number of explanatory variables including constant, that this estimator is unbiased, is an unbiased estimator of sigma squared. Okay? So now we have the estimates of all the parameters of interest. Okay, we have the estimator of beta, and we have the estimator of sigma squared as well. Okay, and now we can formulate the estimator of this variance-covariance matrix, which we have here. Okay, and let's denote this variance-covariance matrix as sigma. Okay, with the letter sigma, maybe sigma b. Okay, the variance-covariance matrix of sigma b. Okay, and now it is natural, in some sense, to replace in this formula for the variance the unknown parameter with the unbiased estimate of the parameter. Okay, so the estimate of this variance-covariance matrix is given by s squared x prime x inverted. Okay, and this is what is calculated by computer programs. Okay, we will see in a moment how it looks like. Okay, notice that this estimator, the estimator I gave the formula for, is an unbiased estimator of the variance-covariance matrix. Indeed, the expected value of sigma hat b is equal to the expected value of s squared x prime x inverted. But now x prime x inverted is non-random because x's are non-random, so the function of x's is also non-random. So this is equal to expected value of s squared times x prime x inverted. But we already know that the expected value of s squared is equal to sigma squared. Okay, so we have sigma squared x prime x inverted. So indeed, this estimator is an unbiased estimator of the variance-covariance matrix. Okay. Now, now we will look on the output from Stata, just to have an idea how this estimators I was talking about are reported on the output of the computer program. Okay. First of all, we already know some elements of this output. Okay. Here we have the table with the estimates of coefficients. Okay. The estimated coefficients are in this column. Okay. Here the model is the model in which we are modeling the production function. On the left-hand side, we have the logarithm of GDP, actually production function for Poland. On the right-hand side, we have the labor, okay, so the number of people working, actually the logarithm of the number of people working. R is the interest rate, and T is the time trend. So basically, the variable which is taking the value 1, 2, 3, 4, and so on. Okay? And now, we know that S squared, we know S squared, okay? The S squared is the variance, is the estimator of the variance of the error term. Okay? Actually, this sum, which we have here, is the sum of squares of residuals. Okay, the sum of squares of residuals, this number is here. Okay, here we have the sum of squares of residuals. Okay, it should be divided by the number of observations. Number of observations is there, so 39, minus the number of explanatory variables. Here we have 1, 2, 3, 4 explanatory variables. We include constant as an explanatory variable. Okay, so here we have the estimate of the variance of the error term. It is sometimes called mean square error. Mean squared error. Okay, and now the root of this. Okay, so basically the estimate of sigma rather than sigma squared is just the root of this number, and this is reported here. Okay, so here we have the estimate of the standard deviation of the error term. Okay, well, not the variance, but the square of variance. Okay, so the square of variance is the number which we have here. Okay, so this is basically square of S squared. Okay, and now the variance-covariance matrix. So there is a special command in Stata which you can use to obtain the this variance-covariance matrix. Okay, so the estimate of the variance-covariance matrix of the of our OLS estimator. Okay, and you have this matrix reported here. Okay, notice that only the elements on the main diagonal and under the main diagonal are reported. Okay, why so? This is because this matrix is symmetric. Okay. By the way, this matrix, okay, this estimator is an estimator of the variance-covariance matrix. Variance-covariance matrix is always a symmetric matrix. Okay, so it makes sense that the estimator of the matrix which is symmetric will also be symmetric, and it is symmetric. Okay, so Stata kind of communicate the matrix is symmetric by reporting only lower half of it. Okay. Obviously, other elements, the elements which are over the diagonal, can be deduced from, analogic, the elements which are under the diagonal. So for example, here in this place, we just have this number. Okay, we know that the matrix is symmetric, so here we should have this number. Okay, here we will have this number, and so on and so on. Okay. Okay, so now we will talk about how to estimate the linear combination of the parameters. Okay, so sometimes